But don't do it again.
Go ahead.
So I am Nothingface, and this is to talk about automotive networks. A little overview. No, it's not. Is this yours? A little overview of what the talk's going to be about. Going to give a little brief background about myself, give you some perspective about, get some idea of my perspective, and just give you an idea of where my, the ideas that I'm coming up with may or may not be based on my strengths and weaknesses. Give you a little idea of how this could be relevant to you, depending on your level of interest in hacking an automobile. There's some things that may be interesting to you, even if you aren't interested in hacking an automobile, just to learn about the operation and understand what's going on. Give a little bit of background on the electronics in automobiles, and then large part will be about OBD2. It's Onboard Diagnostics 2. That's a standard used commonly today. Talk a little bit about common places that's used, the physical and data link layer, trying to adhere somewhat to the OSI model of networking. Talk about some of the diagnostic modes that specifies, some products that implement it, and then I'll conclude with an introduction to some software I've been working on to implement these protocols and serve as a platform for others to develop other applications. So about the speaker, I'm educated in electrical and computer engineering. I have professional experience in hardware and software design, but I'm also a Saturday afternoon mechanic, so I'm not afraid of grease or wrench, but I'm also not a mechanical engineer. So the automotive engineering aspects are where aren't so much my strengths, but my hope is to be able to put tools in the hands of those who are more able to make those types of automotive engineering decisions and tinker with their vehicles. And I'm also concerned about privacy, and as you'll see, there's a number of aspects of the buses and the networks on the vehicle that could potentially have privacy implications. So why should you out there in the audience care? Well, the automotive maintenance monopoly is probably the big reason. For automobiles, you can get service manuals that provide mechanical drawings with great deal of accuracy for all the mechanical components in a vehicle, every bolt, every nut, all the torque specifications, all of that. But for as far as electronics go, generally the best you can get is a wiring diagram that tells you where the wires in the vehicle go to hook up one box to another, but each box is a black box. There's no schematics of the boards, there's no source code to the firmware. There's limited protocol specifications, so there's no way to really do the same thing you can do with an engine with the computer that controls the engine. And particularly from my background, I think that's very limiting, because I'd like to be able to tinker around with that. So a lot of this is more reverse engineering to sort of try to gain that knowledge from a vehicle. There's also privacy implications, even if you're not interested in tinkering with a vehicle. There are things that a vehicle could potentially be recording with a lot of electronics on there. It could be recording, storing, transmitting data about your driving, about your vehicle, and all sorts of information about the driver of the vehicle. And so, considering all these things, modern vehicles tend to be more under the control of a manufacturer than the owner, and there's some barriers put in place to prevent you from being able to control that, which a lot of people may object to. I personally do. Automobile electronics, where did that come from? Well, initially it started originally under the hood, just controlling fuel injectors, analog brakes, traction control, airbags, performing some of the more advanced functions that were a long time ago done by mechanical or electromechanical systems, but as federal requirements got more strict, and also as the systems got more complex, the need was to make it more of a software type system with a software control system. There's also user visible systems as electronics becoming cheaper and more used. They're used for climate control, entertainment, navigation, communications, and so onboard diagnostic standard, OBD or OBD1, was an early standard by the federal government in the United States to standardize on some of these electronics, but the standardization only went so far, and it didn't actually require the manufacturers to standardize a particular implementation. It just said certain functionality was required. So that led to a number of disparate implementations in the field. So every manufacturer had a different test box that you need to get a specific one for a specific vehicle to perform the same functions. So onboard diagnostics 2 is a standardized implementation that said not only do you have to do particular features, but you have to do them in a particular way so that you can have interoperable products where you can get a test box outside the vehicle to plug it into any vehicle and it will communicate with it, and you can also get replacement parts for certain pieces in a vehicle. But, actually, I'm going to save questions till the end, if that's all right. Oh, sorry. So OBD1 was early 90s is when it was standardized, or when it was required. OBD2 was mandated in 1996, and that's current in all vehicles nowadays. There's sort of a little bit of slop in the time frame at which they're implemented. The federal government said vehicles starting in 96 have to have them, but they don't actually have to be fully functional until 2000 or 1999. So there's some variance in what actually has been implemented, and there's some discussion about what's the future for OBD3, so I'll get to that a little bit in the future as well. So the current standard is OBD2. It's standardized by SAE, and the standard covers a physical connector. All vehicles have to have the same single physical connector. It covers a data link layer. There's 3 options where any vehicle has to have one of the 3 options, and there's a standard network protocol that's run on top of all the data link layers. It also standardized diagnostics, by which there's certain procedures and mechanisms required for diagnosing, troubleshooting the vehicle. Only the diagnostics that relate to emissions control systems by U.S. federal law under EPA legislation are really required. The scope of the standard covers the ability to use this bus for other purposes. So there's room in the standard to support standard common components and manufacturer-specific components, but those aren't required by the federal law. There's also many packet formats and data types for diagnostic data. Again, there's a variety of them that only a few of them are specifically required, but for manufacturers that don't want to duplicate efforts and have a separate diagnostic bus for all the things that are not required, they can just use the same bus for all of their specific proprietary parts. OBD2 also specifies a mechanism to read and write the ECU memory. ECU, there's two definitions for that acronym. Originally it standard for engine control unit, but now it's often used to mean electronic control unit, which can control things other than the engine, such as anti-lock brakes or airbags or climate control, or any of those black boxes could be a ECU, an electronic control unit. So since you have microcontrollers or more functional processors and memory, you can read and write the memory with OBD network messages. And there's also a security feature to allow particularly either proprietary or safety-related features to be protected by a security feature that requires certain knowledge of the vehicle before you, say, reprogram your anti-lock brakes or your anti-theft system on the vehicle. And that's not required, but it is used by a number of manufacturers for the theft control systems or anti-theft systems. So common usage. This is the scan tool is one of the very common uses of the diagnostic bus for the purposes, as its namesake, diagnosing problems with the vehicle. An ECU detects a fault condition, some problem with the vehicle as you're operating it. Say, for example, an oxygen sensor detects a mixture too rich. So that ECU, it records a diagnostic trouble code. It's basically just a number that explains more detail about what exactly is oxygen sensor 2 on bank 2 had a problem. And when the diagnostic trouble code is stored, it causes the check engine light on the dashboard to illuminate. Some DTCs can be minor and not cause that to happen, but typically they cause the check engine light to illuminate so that the driver of the vehicle knows there's a problem. They take it to the mechanic. The mechanic plugs in this scan tool device. It retrieves the DTC. This is when people hear mechanics saying they read the codes back or they scanned the codes. This is the process that they're doing to determine what that number is and then use that to troubleshoot the problem. So then they fix the problem, and then with that scan tool, they can clear the DTC, cause the check engine light to go off, and your car's fixed. Another common usage of OBD2 that's only becoming put in use in the last couple of years is a crash data recorder. Now, this is a function where the airbag control module senses a deployment or non-deployment event. The deployment events relate to when an airbag deploys, just the sensors detect the acceleration of the vehicle and impact sensors and whatnot to determine that there's been a crash, and it deploys the airbag to serve its purpose. A non-deployment event is an event that causes perhaps some but not all of the sensors to trigger, so it doesn't actually deploy the airbag, but it's considered to be fairly significant, so that information can also be stored in the airbag controller. The vehicle sensor data is stored in the airbag control module. That's where the actual information is stored, and it can store information from other sensors that are not part of that module, including the vehicle speed, engine speed, throttle position, brake state, the driver's seatbelt state, whether it's engaged or not. And then this information can be read back from law enforcement or mechanic or whatnot, after the crash for analysis. Doesn't help in troubleshooting the car because it's really just information about the crash. So it's more for forensic analysis of an accident, possibly in a legal setting. So if the vehicle is repaired, the airbag control module is just reset or replaced. So getting to the OBD2 network. The physical layer specified by OBD2 it specifies 3 diagnostic buses. There's little mention in OBD2 of other buses. I'll get to that in a bit. But the 3 main buses are these 3 here: the PWM pulse width modulation, the variable pulse width modulation, and the ISO asynchronous serial bus. The ISO bus is actually standardized by the ISO organization in Europe, and that's commonly used by European cars and Japanese cars, but the other 2 are actually detailed specified in OBD2, and any one of the 3 buses is required on a vehicle, and is required to use that bus for all of the federally mandated diagnostics, and commonly manufacturers then extend that functionality to every other diagnostic capability they have, because why add a second bus when you don't need to, we already have this one. Some other buses that are common in automobiles are the CAN bus, the controller area network. That's a lot higher speed than the other buses by about a factor of 10 or more. And the CAN bus is typically used for real-time communication between ECUs on a vehicle, whereas the diagnostic buses are used for communicating off the vehicle to a scan tool or some other device plugged into the vehicle. The CAN buses are often used for communication between the airbag controller and the engine control unit while you're driving the vehicle in real time to update vehicle speed or other sensor readings or to control systems. And CAN is more used in higher-end automobiles nowadays, but its use is becoming more and more prevalent. And I think in the future there's going to be a lot more functionality available on the CAN bus. And other buses that are used in automobiles, there's manufacturer proprietary. There's the OBD1 buses. Like I said, that there's no standard implementation, so there's a variety of buses that are used for the OBD1 implementations, and there's also buses before OBD1 where manufacturers had substantial electronic control systems in a vehicle, but did not, before there was federal requirements to have certain emissions control systems diagnosable from an off-board controller. So there's a variety of those, and those are limited use from different manufacturers. So the data link layer on the OBD2 and the ISO bus, they're all half duplex shared buses, and they're all carrier sense multiple access with non-destructive collisions. So that, basically what that means is there's a priority in the header of the packet. The beginning of the packet, which specifies the message type and addressing, is allocated in such a way that the higher priority messages will win a contention on the bus. So you don't actually have a destructive collision that causes both packets to retry. Only the lower priority packet will retry, and this basically makes it such that if you have a bus with a lot of traffic on it and a lot of contention, you won't you won't have zero data rate. You'll still be able to have effective communication, but certainly the lower priority messages may get delayed or not sent at all. The network layer is a standard across all three of the OBD2 buses. The SAE specification specifies addressing modes. There's two different addressing modes, the functional and the physical. The functional mode is used for addressing a component by its function, as the name says, and that's for the purposes of allowing vehicle manufacturers to have freedom in the topology of how they lay out their ECUs, whether a manufacturer wants to have 1 or 2 or 5 ECUs in a vehicle. They don't need to be concerned with the functional addressing. You can say, you can ask a component, which component has the the sensors for the oxygen sensors, and you don't need to care that the one manufacturer has one ECU that controls that and another manufacturer has 5. You'll be able to talk to all of them. So that's it's more to ease the ability of creating the off-board diagnostics devices. And the physical addressing is sort of a traditional network topology where, typical network addressing where every individual physical ECU has its own address. And either can be used for a vehicle, but certainly the functional can be done on any vehicle very much the same, and physical needs specific knowledge of a particular vehicle. And the network layer is also packet formats. There's also packet formats defined, and they define things such as the diagnostic modes, where you can run tests, you can query sensors, you can control outputs. That's mainly the purpose of the diagnostic bus, is from the point of view of a controller off the vehicle, controlling the systems on the vehicle and for diagnostics troubleshooting purposes. So in these various network formats, there's some data formats that are used to exchange information, and this is done in a fairly efficient way to minimize or to maximize the utility of the low data rate buses. There's sort of two aspects to the defining a data format. One is the scaling limit offset table slot, and that maps the data bits or bytes to a meaningful magnitude. So basically it's what a signed or an unsigned number, the bit width, and it goes even further to define fixed point formats where, for example, an 8-bit value can represent -40 to 87.5 in 1/2 increments. And the parameter reference number, PRN, is sort of the other half to that, where it takes provides the units and a label or description. So a PRN would include something like a vehicle speed in miles per hour, and then it would reference a slot that would dictate how the magnitude is represented. So the slot and the PRN are used to, there basically have to be off-board tables of what packets supply what types of values, what's the slot or PRN for values that come back from the vehicle, so that the vehicle can send back responses efficiently. The diagnostic modes, variety of diagnostic modes here. Like I mentioned before, requesting the sensor or diagnostic data. You can ask an off-board device can query the vehicle for any particular sensor, what the reading is, or diagnostic data, which is perhaps sensor input that's been processed in some way, or the results of an onboard test. It's a freeze frame capability where certain sensors can store their values at a particular time. You can set triggers so that you can manually control when information is stored, where if a certain threshold is reached on a particular sensor, then store all these other sensors. Also, the freeze frame data is stored on some DTCs, the diagnostic trouble codes. When a particular error occurs, sometimes automatically the sensor readings related to that error will be stored, so a mechanic won't need to go reproduce the problem. He'll already have a bit more information about what went wrong. And as I mentioned before, the scan tool example, you can read and clear the DTCs. The onboard monitoring and diagnostic tests, there's there's continuously monitored and non-continuously monitored systems, which are fairly self-explanatory. One just repeatedly runs as the vehicle is running, and the other one is sort of a one-shot deal. You ask for the value, ask for it to run, and it runs and gives you a value back. And you can initiate the tests and read the results back from the tests. And some of these tests are also run at particular times automatically, and you can read back the results of those automatically run tests. Some other diagnostic modes available are reading vehicle information, which includes the VIN, calibration data, memory checksums, and even more generally just reading and writing memory to the ECUs, which can include data parameters. It can include code to the runs on the microcontroller that controls whatever the ECU's function is. So what types of existing products are out there? There's sort of a spectrum of the type of functionality and the sort of level of integration with the manufacturers in the products. There's the hardware products that are basically you just buy a box, and they go all the way to the proprietary full interface type things that the manufacturers have. Things to be at the dealer. They're very functional. They have all sorts of, they can do just about anything that you can do on those diagnostic bus, control just about anything, but they're typically in the tens of thousands of dollar range. There's also devices that plug into a PC and just provide basically a network interface to a PC, and then the PC runs software that provides some functionality. Often those are less functional, they're more general, so they support some common subset across vehicles, but they don't necessarily do every little feature of every vehicle out there. And those usually convert some type of serial, RS-232 or USB, into the diagnostic buses. There's also chips, so we're getting down more into the low level. There's chips that provide some of this functionality, which certainly could be the basis for the devices. And there's also a few designs for real simple schematics or kind of hacks on the RS-232, TIA-232 serial port that will communicate with the ISO interface. The ISO interface, the bus, again, that's the bus that's defined by the ISO, but SAE references it sort of as a consideration to the European and Japanese car manufacturers that tend to go with ISO as opposed to SAE standards. And that data link layer is looks roughly similar to what's UART, a serial UART interface. So with just a physical layer conversion, you can actually plug a serial port on a PC into that. So then with some of these devices that are just hardware that plug into a computer, you need software on that, certainly. So there's numerous commercial and shareware products. Standard support is most common, sort of the common subset that does the most number of vehicles, but doesn't do all the features, the new features of the vehicles. And some of them, there are a few that are manufacturer specific, and those are more commonly the commercial products. And there's one notable free software project called FreeDiag. That provides basically the basic scan tool operation and diagnostic procedures. It does not go into calibration of vehicle-specific things, nor does it really. There is some support for diagnostics on some proprietary buses, but there's not too much support. Certainly not the spectrum that's available from shareware or certainly commercial software. So OpenAuto is a project that I've been working on, and this is a bit of an overview of what that encompasses. I've been working on some hardware designs, another sort of variation on the TIA-232 to ISO bus interface to make use of some new chips that are fairly available now, fairly cheap. It's somewhat of a low part count, sort of easy to manufacture design, or easy to put together. I mean, you could, with 2 parts and samples from a couple manufacturers, you could, put that together by soldering 10 wires. So it's a pretty simple design. I'm also working on a repurposed USB serial adapter, basically taking a keyspan USB to RS-232 interface and writing custom firmware that will talk not only the ISO out of its RS-232 connector, which would be fairly easy to do, but also doing the VPW and PWM so that you can support all 3 of the OBD2 diagnostic buses with one device. And that's That's not complete, but I've been working on that the last few weeks, so that's sort of in progress. And software is a layer 2 and a layer 3 network stack, and some application software. The network stack is in sort of early alpha stage, primarily of use to develop, well, really only of use to developers. There aren't, just have test applications written, no scan tools or any diagnostic control, but it serves as a basis. It could serve as a basis for writing such applications. The approach taken by all the software packages that I've seen is to basically write one single monolithic application that talks all the way to the device, to the user interface in one single application. And what I'm trying to, my sort of theory of operation for Automotive is to provide the standard network stack type of software where each layer of the network is a separate piece of software, is a separate library, so that you can stack them up and you don't have to duplicate efforts when you want to write a new application. You can build on top of whatever standard layer that you're trying to work with. And all of the hardware and software designs are free software released under the GPL. So the network stack, trying to go for a common API across networks. Currently I'm working just with the ISO, but I'm planning to support VPW, PWM, and CAN, at least initially, and then depending on what I can get access to as far as some of the other older buses, I hope to be able to support that, at least to have an API that can communicate with those if others would be interested in supporting that. It communicates the OBD2 data link layer. There's one for all of the well, there's one that corresponds to each of the physical layers, so as the physical layers are implemented, so will be the data link layers. And then the network layer, initially I'm concentrating on OBD2 because standards are available, but manufacturer extensions should be easily added if that information can be reverse engineered or otherwise obtained. And the applications, these are not written. These are just in the planning stage. But certainly a scan tool would be like baseline type of device that is commonly done elsewhere, but would just sort of prove out the network stack. And a network probe and logging tool would be things like TCP dump, Nmap, just standard network diagnostic tools that are common in LAN networks, but would be certainly useful in automotive network too. But the automotive network hasn't been really approached as far as a data network. It's more of a thought of as sort of in a different frame of mind, but I don't think it needs to be. So I think those tools would be very useful. So plan to get to those at some point. And that way it sort of help in determining some of these manufactured proprietary extensions where you can explore unidentified ECUs. If there's some ECU that never responds to you when you do any of the standard communications, but if you if you just go through all the addresses and you can find that it is there, perhaps it can serve some function. So they'll let you explore that, and also explore unknown packet formats. Put a sniffer in between one of the manufacturer's tools in the vehicle and log all the data, and then use that to reverse engineer their protocol, and then implement that in OpenAuto. Also, some ideas for high-level monitoring and control, where you can expand the diagnostics beyond the minimal set for OBD2. Potentially have some type of real-time logging that will just continually, as you drive, will tell you conditions that are not so severe to cause a DTC to be triggered, but potentially can alert you to a degraded operation of your vehicle before it gets to the point of a component actually failing. Logging for whatever purposes, if you want to for more diagnostics, or if you want to tune your vehicle, if you're trying to just determine performance data, you want to generate logging over time, to be a convenient way to do that. Even things as wild as a configurable UI for a detailed dashboard where you take all your gauges out and you put in an LCD, and then each driver can have their own theme and have their own gauges displayed however they want. They can have, someone can have just the speedometer, and other people can add the output of other sensors if that suits their driving style. So that about wraps up the onboard diagnostics and automotive networks. So I guess I'll open it up for questions or comments. Yeah.
Can you access the CAN bus through the ODD configurator now?
The question was, can you access the CAN bus through the OBD connector? And yes, you can. The SAE standard for that connector also specifies a standard pinout. And that pinout says, basically, if you have the ISO bus, it has to be on this pin. If you have the VPW bus, it has to be on this pin, PWM bus on this pin, and the CAN bus on this pin. It doesn't have any other mention of what you would use a CAN for, but it says if you have a CAN, it should be on these pins. So it should be there, and it should be in a standard place. So since the CAN bus is standard, you could potentially have a generic sort of network layer there to communicate with whatever you can find on the end of that bus. Other questions? Yeah. Sorry. Was the question, can you add new devices onto that bus? Certainly the Open Auto architecture is just a network stack that communicates on this bus. So if you allocate the address for your ECU to be in the range not for the off-board scan tool, but for an onboard in the onboard range, and you don't obviously collide with an ECU that's there, which shouldn't be very hard because there's a few hundred. I think it's a 7-bit number, so about 128 addresses, and most vehicles have less than 10 ECUs, so there should be plenty of addresses to pick from. But yeah, it certainly could be possible to add an ECU to the vehicle and communicate on that bus. Yeah, sure.
Can you talk more about the privacy issues? Like if you got a rental car, what can you tell about the history of that car?
If you had a rental car, I don't know that there would necessarily be a lot you could tell. Depending, I mean, there could be some with OnStar and some navigation systems. There might be some proprietary ways you could look through the history of it. One thing you would most likely be able to tell is with the crash data recorder and the airbags, you wouldn't get a very detailed history, but you could tell if there had been a non-deployment event. Basically, if someone was reckless driving almost to the point where the airbag deployed, but not quite, you could read back those parameters, whatever is stored on that vehicle. But other than that, there's not a lot of logging, no other logging that I'm aware of in the commonly used in ECUs in a vehicle. So there wouldn't be a whole lot of history available, I guess. But certainly that could change with more navigation systems that would give you things like position and time information, and also the availability of more storage to be able to just log all that and not worry about using up storage space. Sorry, Rear? Sorry, the question?
That lets somebody in a remote location determine where the car is.
I guess the question was, how can you tell if there's some sort of remote transponder on a vehicle? Those, I guess there's a number of obvious signs of that. Certainly if it has OnStar, that's a capability of OnStar to be able to do that. I believe Ford has a similar system it's more of their navigation system that has some sort of a crash recovery feature that's not used for asking for directions, but in the event of an accident, supposedly it can report your telemetry information for rescue. But those are the only ones that I'm aware of. I mean, there's certainly a number of ways that I could probably think of about half a dozen off the top of my head of ways you could potentially set up a telemetry system on a vehicle, but I don't think there's no OBD2, there's no SAE standard for that type of system. So it's really just up in the air. It could be implemented any number of different ways. There's not a besides the ones I mentioned of the OnStar and whatever's Ford similar corollary system would be. I don't know of any other commonly used systems that would do that. I guess, so that reminds me of one more, just a little bit about sort of the privacy and the telemetry information is so this OBD2 is the current standard for, that's a federally mandated standard from the SAE for automotive diagnostics. There's been some talk about what will be OBD3, what will replace it, and I haven't seen anything concrete. I've seen a lot of sort of rumors and discussions in trade journals, but I have seen, the only concrete thing referring to this I've seen is on the California Air Resource Board, which is sort of where the EPA gets its direction for what eventually becomes a nationwide standard. And they mentioned that there's going to be a feature, or there's considering a feature that will make your vehicle inspections be much more convenient by continuously, automatically reporting the operational state of your vehicle to remote transponders, such that only the vehicles that are performing under spec will be required for an inspection. So certainly that could be have all sorts of privacy implications if your vehicle is all the time or once a month is reporting its information to these beacons around your city or around your town. It could be reporting more than just emissions control data. It could be required, by the time OBD3 comes out, it could require GPS in your car, and it could have your coordinates. Certainly have to identify your vehicle, and, I'm sure that someone will eventually find out how to decode that themselves, and then you can just track people very easily with that, that type of system. What's that?
Or substitute your own data.
Well, substitute your own data. Certainly, yes. You could do that. You could make a transponder that continually just reports, yes, my vehicle's fine, everything's perfect. Just kind of get a record of what the proper operational message is, and then just continually play back that forever and disconnect the real transmitter. So there's certainly a lot of flaws in that system, and I'm not sure how much of any of that is being thought out, because all I've seen concretely about it from authoritative sources is just a very vague comment on the California Air Resource Board site. Sorry, more questions? Yep.
You mentioned that the computer is storing the vehicle ID number. What does this do to the repair industry, where it's pretty common practice that if the computer fails, they just go to a salvage yard and get it done?
The question was, the ECU stores the vehicle identification number, so what does that do for aftermarket mechanics that will swap ECUs for vehicles that have been damaged or need to be repaired? That can cause a significant amount of a problem, I'd imagine. I know I haven't seen anything with reference to the VIN, but I know there's a lot of problems with odometers that with when you use an ECU that has because the odometers in a lot of vehicles nowadays it's displayed on LCD, and it's information stored in an ECU in memory somehow, and so there are ways to reprogram them a single time, or certain procedures you have to go through to get them to be reprogrammed. And I imagine they'd be similar for the VIN, but I also imagine that it probably will be very difficult, because I know that in other for anti-theft systems, there's sometimes there's pairing of certain electronic components where certain ECUs will only work with their corollary ECU. Specifically, the vehicle I drive, there's trouble putting in a replacement engine, because you have to put in a replacement ECU at the same time you put in a replacement engine. Otherwise, it just won't work. So you can't replace your engine or your ECU separately. You have to replace them both together. Other questions? What? Yeah, they can do OnStar. They can do all sorts of things remotely, which makes it kind of scary. They can read back just about anything from the vehicle. I mean, they can start your vehicle remotely over the phone. So it's. I actually had a discussion with OnStar salesperson one time about some of the privacy and security of that, and their best answer was, well, we have a policy, and we train our people well, and I don't know any more than that. So personally, I don't trust them very much, because I doubt their policy is enough to really do anything in the face of something going wrong, and I really doubt that they have too much security on top of the system to make sure that it's hard to spoof and do bad things. That question? The question was, on Bluetooth-enabled vehicles nowadays, is Bluetooth on the CAN? I'm not sure. I don't have any familiarity with any of those vehicles, but I would imagine in some fashion there's probably some interlock there, so that, for example, if your phone rings, it can automatically mute your stereo, or perhaps they can do even more sinister things like make sure that the vehicle is operating a particular way, or hang up your phone if your car is steered too erratically or something like that. I mean, I don't know. That's a little far-fetched, but I do think that the muting the audio of a stereo when the phone rings is something that would be very likely done. But I'm not sure. That's just speculation. I'm not familiar with that.
A lot of cell phone hands-free kits that you install in cars now that are wired have a line in them that you either run through a relay and drop the switch power, or one of the more higher-end stereos, or a lot of the OEM stereos have a entertainment view line where if the cell phone is in use, it'll actually drop that line and cut the audio from the car audio.
Right, yeah, the comment was that there's a lot of aftermarket stereos and factory stereos have a line that's sort of a relay output to be able to control this function. But I think that's sort of more of an old technology way to do it. And communicating over the CAN bus with a message, it would be, I think, the way things are going in the future. And it's more of a sort of a shared network as opposed to a one wire for every function you need. You have a pair of wires for your CAN all around your vehicle, and that does everything. You don't have to have dozens of wires going back and forth, spidering all through the vehicle. Yes.
Just out of curiosity, do you have any idea how much code is in the software of a typical vehicle, and what kind of memory and processing power they have?
The question was how much code, as far as quantity, is in the ECUs, and what type of processing is in it. Certainly, in say 5 to 10 years ago, 8-bit microcontrollers was very common, and 8 or 32K of memory was very common. I think modern vehicles are still used. Some of them still use 8-bit microcontrollers for a number of functions. Some of the more enhanced ones, and they also have code that's maybe 32, 64K, and they also have a number of ECUs. Instead of having one ECU with 8K of memory, there's 5 ECUs, and each one has 32K of memory. So they sort of parallel in that sense that there's multiple each serving separate functions.
The average processor is about 40 megahertz.
The comment was average processor is about 40 megahertz and 1 to 2 meg of storage. Yep.
Would it be possible to scan like a OnStar frequency, such as you would like in a wall driver or something? Could you scan for OnStar?
It's cell phone. Yeah.
And CDMA now, OnStar, the newer versions are CDMA.
The comment was the newer versions of OnStar CDMA, but I do believe that they do their data in band in their voice channel, because the demo I saw, when they called up the OnStar representative and told them that they locked themselves out of the vehicle. Since they're calling from the vehicle, the OnStar person said, "Let me disconnect you for 10 seconds," and they disconnected. The doors unlocked, and then they came back on the line, reconnected the voice conversation. So I believe that there's probably doing some type of audio frequency shift keying through the voice channel, or some other type of modem through the voice channel of a cell phone.
So next year you'll have that encoded.
Hopefully.
Have you heard more about cryptography on the buses?
The question was, have I heard more about cryptography? Oh, sorry, was there more than that? Yeah, so the cryptography on the buses, the only thing I know as far as any type of security feature is the security feature in the OBD2, and that's really just a challenge response type of, it gives you a seed and you have to give it back the corresponding key, and those are 16 bits each way, and that's the only security that I'm aware of that the vehicles do. I think some of them also have a security through obscurity, where they have a checksum in an odd place in their memory map, and they have an algorithm that's people don't know, but it's not really I doubt it's a cryptographically secure algorithm. It's just an unknown algorithm. Because I know a number of people that have reverse engineered different ones. So if the fewer vehicles that have a particular algorithm on it, the sort of the less interest there is to reverse engineer it. And I don't know, it's terribly effective, but I think that there's very, very crude, and it's hard to really even call what they do cryptography. Sorry, another question?
What kind of storage devices
The question was, what type of storage devices do they use? EEPROM is commonly used because you need to be able to store small amounts of data. You don't. A flash memory wouldn't be sufficient because a DTC is 2 bytes. Some of the freeze frame data is just a few bytes, so they need to be able to store those periodically, and also share the memory with storing calibration data, which is only written once in the factory or whatnot. So the EE electrically erasable proms is what they use. Other questions? Yeah.
For open auto, have you considered writing the driver for the USB or like an OBD device driver?
The question was, have I considered writing it as an OBD device driver? I'm not quite sure what the what you're asking, but I think that is basically what I'm doing.
Put it in the kernel as a device driver that can file system, so any applications can open it up.
Yeah, the question was, or the comment was to have it as a kernel device driver, just like as a network interface, like other network interfaces in the vehicle. And yes, I have considered that, and that's sort of, I see that as like a later step to what I'm doing now, just because of the ability to develop it, and some of the common reasons why one would want to do that for normal network interfaces isn't so much of a concern for OpenAuto, things like performance, and some of the other integration with the other utilities where you're not going to run, well, I suppose you could. It would be, I don't see what, there wouldn't be a high priority to tunnel IP over OBD2, but potentially you could do that if you had something set up, and that might be an interesting thing to play around with. Yeah, certainly. That's actually something I've been thinking about too, where you could have some sort of small device on a vehicle that talks OBD and has Ethernet or something that you can connect through a computer in the back of your vehicle, or tunnel it over 802.11 out to a service shop or something like that. But yeah, I have considered that, but I see that sort of as a later stage to just getting the driver stable, because there's not a lot of benefit to doing it at this point, and just would complicate the development cycle. Other questions? All right. Thanks. That wraps it up. Thanks a lot.